So those famous quantum numbers provide an unambiguous means of addressing each and every electron in an atom. We left our hero grappling with those complex words: principal quantum number, angular momentum quantum number, magnetic quantum number, and spin quantum number. And here's where I'm just going to flesh that out a little bit, and then we're going to move on to a more periodic table-based and graphical-based representation of these electrons. Obviously here, if we start with hydrogen, the simplest atom of hydrogen, one proton, no neutrons, one electron, and that electron then occupying the lowest energy level, level 1, principal quantum number, and an s orbital, spherically shaped. Remember that if our angular momentum quantum number is equal to 0, then our magnetic quantum number is also equal to 0 because it can't take on any different orientations. And by convention, the first electron into that orbital that can hold a possible 2 electrons is given the -1/2 spin. So those 4 then quantum numbers uniquely define and describe the electron in a hydrogen atom. If we move to a helium atom now, we have 2 electrons. Notice that the quantum numbers for the first electron are the same as they were for hydrogen, in the sense that it's occupying the same address in a helium atom. The second electron needs to be 2 in a neutral helium atom, is going to take on a slightly different address in the sense that it's still going to be at the first energy level. It's still going to be in that s orbital with an angular momentum quantum number of 0. It is still, of course, going to have a magnetic quantum number of 0, since, again, no different orientations are possible for a sphere. And it's going to have the spin quantum number, if you remember from the last video, of +1/2 to correspond to its opposite spin. And we have now a pair of electrons occupying this orbital. And that pair is going to be an important concept because the pair fills the orbital and results in essentially a lowering of system energy, which is favorable. And we're going to see that this tendency for combining atoms to fill up orbitals is going to be an important theme in chemistry. Not to drag this on forever, but think about lithium then. Well, before I do that, look at your periodic table. I think I got one here somewhere. And wow, note that the first period of the periodic table only has 1, 2 boxes because, of course, only 2 electrons are allowed in any given orbital, and at the first energy level only 1 orbital is possible, and so we end up with only 2 elements. Hydrogen with 1 electron and 1 proton, helium with 2 electrons and 2 protons occupying that first period. If we need 3 electrons in our atom, we got to go to the second period where more housing is available for electrons. Okay? So lithium then, 3 electrons. Notice that the first 2 electrons have exactly the same address as the 2 electrons for helium because they're living in the same place that the electrons were in a helium atom, only they're occupying a lithium atom. The third electron, notice, now has to go into the second energy level, right? Because there is no more room at the first energy level. It is going to occupy, again, an s orbital. And because the angular momentum quantum number is 0, the magnetic quantum number must be 0. And by convention, again, taking the -1/2 spin as it goes into that location. And so here then the address for each of the 3 electrons in the lithium atom. Notice that 2 of those electrons live at the first energy level, and 1 lives at that second or higher energy level. Remember the correspondence between energy level and energy, right? Obviously, we can do this forever, and the lists of electron locations just get longer and longer and longer. And the higher up we go, the more energy levels open up, and we can have more complex series of quantum numbers, which will demonstrate as we look at the possibilities farther on down the line. What we're essentially doing, though, is sort of building up these atoms by respecting a couple important principles that I'll talk about in just a minute, and putting electrons in their possible locations based on those principles and the energy levels of them. Another view of this thing is to talk about the electron configuration of various atoms of elements. And we can make the correspondence between this configuration and the periodic table quite easily, and that becomes an important skill in this part of the course, to be able to look at the periodic table and see the status of the electrons in that view. As I said before, we're adding electrons one by one to build larger and larger atoms of different elements. And obviously energy is going to be an important thing, and we're going to represent these energy levels on sort of a graph paper kind of thing. We're going to use boxes to represent these different sublevels, right? Remember that if the angular momentum quantum number is 0, you have an s orbital, and only one possible orientation is available, and so our magnetic quantum number has to be 0. If we have a p orbital, we now have 3 possible orientations. So if our angular momentum quantum number is 1, we can now have magnetic quantum number equal to -1, 0, or 1, and away we go. So it gets a little more complicated, but most students find that once I move to the graphical approach and represent these sublevels as boxes, the whole thing works out quite a bit easier. In that box view, we'll often represent the electrons as simply being arrows. One of them will be pointed up to indicate a positive spin quantum number, the other one pointing down to indicate a negative quantum number. Once again, another representation of the shapes of these things. There are lots of wild and colorful things out there on the internet if you want to have a look. But for our purposes, the s orbitals are spherical, the p orbitals are the dumbbells with the 3 different orientations. The d orbitals are, of course, the double dumbbells with the 5 different orientations, and the f orbitals down here. This does, in fact, correspond directly to the families of the periodic table. The s orbital can hold 2 electrons, and so there are 2 columns of the s block in the periodic table. We'll talk a little bit about helium. Note that there are 3 different orientations for the p orbital. Each can hold 2 electrons, and so there are 6 possible elements in each, and indeed they'll correspond 1-to-1 to the p block of the periodic table, and as well down the road. More on that later. Here it is right now. Your first kind of view of the correspondence between the periodic table and the quantum numbers. For the purposes of electron configuration, it's convenient to take helium and put it right here, because in terms of the electron configuration, helium is part of what we call the s block elements. Those in the first 2 columns. Each of these then represent atoms for which the highest occupied energy level is in the s block, or s configuration, the spherical orbital. Once we get rid of helium over there, you should be able to see that these elements here are in the p block. 3 different orientations, 2 electrons in each orientation, giving us a total of 1, 2, 3, 4, 5, 6 possible electron configurations. And indeed, if we get rid of those 2, here in the middle is, of course, the d block, d corresponding to the highest occupied energy level. Note there are 5 different orientations, giving us 2 electrons in each, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 total possibilities. And down here, where we rarely wander, we have, in fact, the f block. Total of 7 different orientations, 2 electrons in each, and if you were to be so foolish as to count those boxes, you would discover there are 14 of them. And so in that sense, the shape and the configuration of that periodic table is a direct result of the way in which electrons fill energy levels and the critical importance of electrons to chemistry and the interaction between those elements. We'll continue to develop that theme in the next video.